Imagine a force so powerful that it can carve entire mountains, create deep valleys, and reshape continents without a single explosion. That force is ice. How can something as soft as snow eventually become powerful enough to cut through solid rock? The answer lies in glaciers. The breathtaking valleys of Kashmir, the majestic fjords of Norway, and some of the world's sharpest mountain peaks all have one thing in common. They were sculpted by moving ice. Thousands of years ago, giant rivers of ice transformed Earth's surface. The evidence is still visible today in the mountains, valleys, and lakes around us. What if I told you that glaciers act like giant bulldozers, sandpaper, and transport trucks, all at the same time? By the end of this video, you'll understand exactly how. A glacier is an accumulation of ice and snow that slowly flows over land. At higher elevations, more snow typically falls than melts, adding to its mass. Eventually, the surplus of built-up ice begins to flow downhill. At lower elevations, there is usually a higher rate of melting or icebergs breaking off, which removes ice mass. Alpine glaciers are frozen rivers of ice, slowly flowing under their own weight down mountainsides and into valleys. They are often called rivers of ice. How do glaciers form? Glaciers begin to form when snow remains in the same area year-round, where enough snow accumulates to transform into ice. Each year, new layers of snow bury and compress the previous layers. This compression forces the snow to recrystallize, initially forming grains similar to the size and shape of sugar grains. Gradually, the grains grow larger, and the air pockets between the grains get smaller, causing the snow to slowly compact and increase in density. After about a year, the snow turns into firn, an intermediate state between snow and glacier ice. At this point, it is about 2/3 as dense as water. Over time, larger ice crystals become so compressed that any air pockets between them are very tiny. In very old glacier ice, crystals can reach the size of an adult fist. For most glaciers, this process takes more than 100 years. Types of glaciers. Bearing in mind the combined influences of climate and topography in shaping glacier morphology, the broad range of glacier types at Earth's surface fit into two main groups, known as unconstrained glaciers and constrained glaciers, which are defined as follows. Unconstrained glaciers have a morphology and flow pattern that is, for the most part, independent of underlying topography, whereas constrained glaciers have a morphology and flow pattern that is strongly dependent on underlying topography. Unconstrained glaciers. Ice sheets and ice caps. Ice sheets and ice caps share the same basic form, a broad, upstanding, slowly moving ice dome at their center, with channels of faster-moving ice that transfer mass to their margins. However, they differ in terms of scale. Ice sheets are larger, covering more than 50,000 square kilometers, with ice domes that can be more than 3,000 meters thick. In contrast, ice caps only reach thicknesses of several hundred meters. Here are two more key features of ice sheet and ice cap morphology. Firstly, they almost completely submerge the landscape, with only the tips of mountain peaks, known as nunataks, piercing the ice surface. Secondly, their flow patterns are, at least for the most part, unaffected by underlying topography. Ice streams. Ice streams are corridors of rapidly moving ice in an ice sheet. A feature unique to ice streams is that they are bordered on either side not by bedrock, but by slowly moving ice. Constrained glaciers. Ice fields. Unlike ice caps, ice fields do not have a simple dome-like structure. Instead, their morphology and flow are controlled by topography. Ice fields, such as the Patagonian ice fields, develop in mountainous terrain where the land surface reaches an altitude that enables snow and ice to accumulate. They are drained by large valley glaciers. Valley glaciers. Valley glaciers, as their name suggests, exist within bedrock valleys and are overlooked by ice-free slopes. They are found in many alpine and high mountain environments, including the European Alps, the Southern Alps of New Zealand, the Andes, and the Himalayas, to name just a few. Transection glaciers. Transection glaciers are, in essence, a system of interconnected valley glaciers that flow in several different directions, often in a radiating or web-like pattern. Transection glacier networks develop where bedrock valleys are deeply dissected, allowing ice to overflow the calls between adjacent valleys. Examples of active transection glaciers can be found in Greenland, Svalbard, and Alaska. Piedmont glaciers. Piedmont glaciers have a unique shape. They begin by flowing through a narrow mountain valley, but when they leave the valley and reach a flat lowland area, the ice spreads out widely, forming a large fan-shaped or lobe-shaped mass. Because of this, the land controls the glacier differently at different stages. Inside the valley, the surrounding mountains guide and restrict the glacier's movement. On the flat lowland, the glacier is less confined and can spread outward freely. Cirque glaciers. Cirque glaciers are among the most common types of glacier on Earth, being found in nearly all alpine landscapes that support ice accumulation. Cirque glaciers are either localized to armchair-shaped bedrock hollows on a mountainside or to the uppermost parts of a glacial trough where they flow into larger valley glaciers. Niche glaciers. Smaller in size than cirque glaciers, niche glaciers form where ice accumulates in a mountainside recess, or niche, such as a rock bench, couloir, or depression. Niche glaciers represent the early stages of glacier development and are commonly found in climatically favorable settings, such as on shaded north-facing slopes of mountains in the northern hemisphere. How glaciers shape the land. Glaciers can sculpt and carve landscapes by eroding the land beneath them and by depositing rocks and sediment. Erosion. Glaciers can shape landscapes through erosion, or the removal of rock and sediment. They can erode bedrock by two different processes. Abrasion. The ice at the bottom of a glacier is not clean, but usually has bits of rock, sediment, and debris. It is rough, like sandpaper. As a glacier flows downslope, it drags the rock, sediment, and debris in its basal ice over the bedrock beneath it, grinding it. This process is known as abrasion and produces scratches, striations, in the bedrock surface. Plucking. The bedrock beneath a glacier often has cracks in it that were there before it was ever covered in ice. These cracks may grow beneath the glacier and eventually join with one another. When this happens, entire chunks of rock can break off and be carried away by the ice. Glaciers can also erode sediment. This can happen in many ways, including downward creep of the glacier ice into the sediment, freezing of water in sediments to the base of the glacier, and squishing the sediment around beneath the weight of the ice. Deposition. Glaciers can also shape landscapes by depositing rocks and sediment. As the ice melts, it drops the rocks, sediment, and debris once contained within it. Ice at the glacier base may melt, depositing grate with funding. Glaciers can also move sediment from one place to another when it flows over sediment beds. Additionally, when glaciers' ice melts, the water it generates can move and rework sediment. This is called glacial outwash.